Okay, so here's my little program. I just run 10 million simulations, but we can just run 1,000 to start. So I do this. I've written this to try to make it the formula is explainable and maybe not the best overall way to write this program, but it's fine. So I make a table of zeros like I normally like to start out with, and we're going to fill in the areas into that table for 1,000 trials. Okay. Do a for loop. I generate 6 random numbers, and then those become my coordinates, x1s and y1s.
Okay.
Then I take the distances, just like you had talked about. Can you hand me one of those, the chopsticks? I can point with the chopsticks and so I don't block the computer. Make the 3 side lengths. The area then is just what I call the area is really the area squared. It's 1 instead of a half. It's a fourth times the determinant squared. You'll remember that the determinant is x1, y2 minus x2, y1 of a 2 by 2 matrix. And then my area squared, my area, which is pi r squared, pi times d1, d2, d3 over 16 times the area. Oh yeah, because the formula was, this is the area squared, it was 4. Yeah. Okay, yep. So I got that right. And then I run, at the end I output the max of the simulation, the min of it, the mean, the standard deviation, and then I actually did some what are called bin counts. How many of them is the area from between 0 to 10, so how many in 0 to 1, 1 to 2, 2 to 3, and we see how many of those there are, what percent of our run was there, and then also between 0 and 2. Okay. And then I give you a histogram. Sorry, I may have been off screen for that part. But here's, first of all, here's the histogram.
So yeah, it looks like a lot, say under, I mean, it looks like it's almost, but maybe 900 of, so 90%.
Yeah, it turns out 83% are between 0 and 2, and 93% are between 0 and 10. And then my, what did I do first? Max, min, mean. So the max is, the area was 9,400. Wow. The min, the area was
very small.
Square, although this was area squared, wasn't it?
Yeah. I think the A was area squared, wasn't it?
Oh no, the A is, sorry, I'm getting confused. The A is actually the area of the triangle.
Oh, okay.
Circle, the area of the circle. Okay, so 9,000. How could I have a very small area? What would that mean?
Well, I mean, your points, the points are they're really close together, but they're not on a line, they're sort of spread out.
Yeah, they're really close together, like maybe they formed a really, really tiny equilateral triangle or something. So there you go. So mean, max, and then standard deviation as well as this last number. Okay. So here the maximum was 9,442. And run it again. Oh, and this time the maximum was 198,830.
Wow.
All right.
Whoops. Oh, this time the maximum was 2.6 million. This time the maximum was 102,000.
So it's a lot like the Archer problem where you just have these.
But you can see our bin counts aren't changing 93 that much. 93.9 from 0 to 10 and 83.2 from 0 to 2.
Yeah.
So what's changing in these simulations?
Just the high
outliers, which are huge and just skew the average by a lot.
Yeah, so let's, instead of running 1,000 trials, 1,000,000 didn't take actually that long. So does this remind you of the Archer problem?
Yeah.
Yeah, sort of.
It's just you have most of the data
chance.
is within a normal range, and but then you get some that's just crazily far out there.
Yeah, here our maximum was times 9 so 900 million. But yet 93.17 from 0 to 10 and 83.58.
So those are staying constant.
Those aren't changing that much. Our mean, is that the third one? The mean was 962,000. But 93% are between 0 to 10. So what does that tell you about the mean?
I mean, it tells you that the mean is getting pushed really far out there.
Why?
Because there's actually got to be a lot of these. Because we're running 1 million trials, and Even if there's
You don't need a lot of them. I mean, with a million, if you divide, let's just say it's 10 to the 11th divided by a million, that's still an extra 100,000 for each entry. You can just add 100,000 each entry.
Yeah, but it wasn't 10 to the 11th. It was 9 times 10 to the 11th.
So it's 900,000. It's almost just adding a million to each entry.
So what happened? Look at what our mean was.
so.
So
This
without
one trial,
Right. That one trial.
it's all but 62,000 of the mean.
Right. So that one trial, all by itself, affected the mean. Let's see if let's see what happens here on one more run of this. So this is. Do you think these results will eventually form a normal distribution?
no.
What do you think? Are we going to get a bell-shaped curve?
No, I don't think so.
No, because look, we're at 10 to the 11th again. But 5 times 10 to the 11th. So here our mean is what, 250,000 different than it was before?
Yeah.
So actually this time there must be more really high trials because it would only be adding 500,000.
Yeah, well, how many more would I need of really high ones?
Really, just like 1 or 2.
Yeah, right. But you can see that a number is staying constant. The number from 0 to 10, about 93%.
Yep.
And the number from 0 to 2, 82%. So down at the bottom of the distribution, we do have some stability, it looks like. It's just that every now and then we get these gigantic ones. And why are we getting the gigantic ones?
Because there's no upper limit.
Yeah, there's no upper limit. So what do you think the answer to this is? What is the expected area of the of the circle?
Infinity.
Infinity.
Couldn't you theoretically get points on a line and have infinity? Like if you
Well, that
somehow-
probability is so small. That
Yeah, you're right. It's an interesting question. What's the probability that you're going to get 3 points on a line?
Well,
What do you
I mean,
think
if
it is?
I think it would be 0 because you can't. It's 1 over infinity that you
Right.
can't do it.
Could it happen that you get them?
Yes.
Yeah. What's the probability of it?
1 over infinity.
Yeah. So it's an intriguing question, and it's a great observation. It's theoretically possible to get 3 points on a line and have that triangle or the circle have
Infinite area.
infinite area. The probability of that happening is
1 over infinity.
1 over infinity, and in probability they refer to that as probability 0.
So
But probability 0 doesn't mean
it's not possible.
it can't happen. It still can happen. It just has probability 0.
Yeah.
And so it's an interesting, very interesting question.
Yeah.
All right, good job, guys.